Hey, welcome back, class. Radioactive isotopes, half-life. So, a radioisotope, let's just jump into this lesson. A radioisotope just refers to an element that is radioactive. Radioactive elements. Okay, so to a degree, we could think pretty much everything on the periodic table, to some degree, would have some sort of radioactive isotope. For the most part. What that means is there is another form of that. So remember, isotope means the same element, but something different about it. Usually it means the amount of neutrons, right? And so depending on the number of neutrons, it depends on how its stability, it affects its stability and how the atom stays together. And so effectively what we see is that half-life, exactly what it implies, is 1/2 of a certain amount of time. 1/2 of a certain amount of time. So with that said, if I have 100 grams of something, 1/2 of that is 50 grams. Well, this right here, what I just did right here, we could think of that as being the passage of time. It's just a concept when I write this arrow. It just means that one half-life has occurred, and whatever that amount of time is, we've gone from 100 grams to 50 grams. And it doesn't matter what the sample size is. If we had 10 grams and there was one half-life, then it would break down to 5 grams, and so on and so on. It doesn't matter what you start with. Whatever you start with is always 100% of your sample of anything, really. It doesn't matter if we're talking about elements, we're talking about pizza, slices, it doesn't matter. So with that said, you could also look at this and realize, well, here we start out with 100% of the sample, and here we have 50% of the sample. This is also 100% of the sample. This is 50% of the sample. This right here, this 50 grams, represents 1/2 of the amount. 1/1 would be the total amount we started with. Right here, this is also 1/2, so 1/1 is also 100% the total amount that we started with, and so on and so on. It just keeps breaking down. The fraction just continues to break down. So let's work on some problems. So we've got a 100-gram sample of arsenic 81, and it's decaying to 6.25 grams. How long is that going to take? That's what question 1 is asking us. And if you don't remember that AS is arsenic, you just simply come back to your periodic table. Remember, you find AS, there it is. We know that it is arsenic. So we've got our 100-gram sample. So let's think about this. We start off with 100 grams. There is a half-life. We break down to 50 grams, and then that's going to break down to 25 grams, and then that's going to break down to 12.5 grams, or I'm sorry, that would be, 12.5 grams, right? And then that's going to break down to 6.25 grams. And you can think of it as money. If you had $100, half of that is $50, half of that is $25, half of that is $12.5, and half of that is $6.25, or $6.25, right? So it's the same thing, same concept. So what we see here is we have a total of 1, 2, 3, 4. We have 4 half-lives. All right, 4 half-lives. Now, to answer this question, we need to know what is the half-life of arsenic 81. So the half-life of arsenic 81, this equals 33 seconds, all right? So all I did was look this up. If you do this enough, then you know it. I just went and looked it up. So if you're ever in a situation where you have something like this, you're not given information you need, you simply research it and find out. And that's what I did. I just researched it. All right. So we've got 4 half-lives. Each half-life is 33 seconds. So if you think about that, that is 4 times 33 seconds. And then, so 4 times 33, 4 times 3, that's 12. So that'd be 132 seconds. All right. So there's our answer. We have 4 half-lives, 4 times that. If we wanted to do it using dimensional analysis, where we show everything that is being done, we would do the same thing we would do if we were converting inches to feet, right? So just like if we had 36 inches, how many feet is that? Well, we know that there's 12 inches per 1 foot. Same unit on top and bottom would cancel out. And so this is really 36 feet divided by 12. And we know 36 divided by 12 would be 3 feet, right? So I just made this up I just made that problem up real quick. But this entire process that I just did right here, this process here, we refer to as dimensional analysis. In other words, it's just a way of converting units. Well, we could do the same thing here. Knowing this conversion factor, we would put half-life, and for every 1 half-life, that's a total of 33 seconds. Well, you can see half-lives goes away, and now you can see how this problem here looks exactly like that problem. So that's where I got that from. Anytime you do this type of math, you're really doing this type of math. All right, so that's what we're trying to get you to see in courses like this, is that it does equate to what you do in real life. All right, it does translate. All right. All right, so next problem here. So how many minutes would it take for a 10 milligram sample of selenium-83 to decay and have only 1.25 milligrams, right? And so selenium-83, here we're told the half-life, the actual amount of time for the half-life, which is 25 minutes, all right? So we've got a 10-gram sample. 10 milligrams. 10 milligram sample, right? And this 10 milligram sample, it's going to break down to 5 milligrams, and then that's going to break down to what, 2.5 milligrams. And I guess if I'm going to keep my significant digits, because I started off with 3 significant digits in the original number, then I'll keep 3 significant digits every single time, all right? And then, so yeah, we're back down to 2.5, and we ultimately need to get to 1.25, right? So 1.25 milligrams. All right. So you can see here that we have a total of we have 3 half-lives, right? So we've got 3 half-lives, and we know that for one half-life, this is a total of 25 minutes. Same unit on top and bottom cancels out. So 3 times 25, 75 minutes. All right. Let's do a couple more. Charcoal. We've got an ancient campfire here. Hang on, I had to get that sip of coffee. All right. We've got campfire here, 1/4 of the carbon-14 as that of new wood. About how old is the charcoal in the campfire? So in other words, how old is the campfire? About how old is a charcoal in the campfire? Let's just go with how old is the campfire. All right, we could go with that. or we could just say the charcoal in the campfire. I probably should have just said that instead. Okay. It's just a typo. I'm just noticing it. No need to redo the video. You get the idea. All right. So if you think about it, now we're dealing with the concept of fractions, but it's the same thing, right? So if we start off with 100% sometime in the past, that would be that. And then eventually it would break down to 1/2 of that, and then eventually it would break down to 1/4, which is what we're getting to. So this is a very quick problem here. You see that there are a total of 2 half-lives. You're told that it's a total of 5,730 years for each of these half-lives. So there's 5,730 years here, and there's 5,730 years here, right? So we've got 2 half-lives and one half-life. There's 5,730 years. Multiply that twice, you'll get 11,460 years. So about 11,500 years ago, that fire was burning bright. All right, let's try one more. All right, we've got 80 grams of some sort of isotope, some sort of elemental isotope that's undergoing decay, and every 4.5 hours it's going to have half of that amount. That's what the next sentence tells us. After 45 hours of time, how much of the radioisotope remains? All right, so if we think about this for a second, so 4.5 hours times 10 would equal 45. So this lets us know here the number of half-lives that we actually need. So we need 10 half-lives, right? So if we start off with 80 grams, that's going to break down to 40 grams. That 40 is going to break down to 20 grams. That 20 is going to break down to 10. And it just keeps breaking down to half. So far you should see here that we've got 1, 2, 3, 4, 5 half-lives. So we're literally halfway to where we need. So we just need 5 more half-lives, right? So after 2.5, that would be 1.25 grams. After 1.25, half of that would be 0.625 grams. Half of that would be 0.3125 grams. And I'm just going to bring this down. All right, 0.3125 grams. Half of that would be 0.15625 grams. Nothing to memorize. Literally just put in your calculator, hit divided by 2 each time, press enter. It gives you your answer, right? So that's 5, 6, 7, 8, 9. We need one more. And then, so half of this would be 0.078125 grams. All right. So, 80, right here, we're looking with about 2 significant digits. So we could do the same thing here and say 2 significant digits would be those 2 digits right there. So we're looking at there remaining probably 0.078 grams if we were to go with significant digits. This entire number here, that's the actual number, right? But, you know, this 1 here is not going to round that up. So it doesn't really change the value of our answer that much, right? Just for general purposes, 0.078 grams makes sense. And so just so you know, you can see some things here that where, you know, carbon-14, we had 5,730 years. This here is just a number of hours, right? Go back to a previous problem we had, and that was a number of seconds, right? So we come back here. Remember, we had a number of seconds here. Here we had a number of minutes. Come back to where we currently are. Then I'm just letting you know, there are things that have half-lives of millions of years and billions of years. So it doesn't matter what the unit of time is, the process will always be the same. But these things that have short half-lives for hours and minutes, what's really important to understand about all that is, how this works with medical technology. So if you think about it, if something has a short half-life of so many hours, that makes perfect sense. If you go to get something done at a hospital, let's just say instead of doing some surgery to cut you open and to take a look on the inside, it could be that by understanding how something is working or not working inside of one of your body's systems, that a doctor can better diagnose maybe some health issues that are happening, and then prescribe treatment and come up with a treatment plan, right? Prescribe medicine, come up with a treatment plan. So for instance, if you've got some sort of, say, digestive issue, you may do a test where they have you drink something that, and then have you sit in a various machine and get a scan on the inside. And what they're doing is a CT scan. And what they're really doing is they're taking an image of the radioactive energy of the isotopes in the substance that you drank, and as it moves through your body's digestive system, and as your body is processing it or not processing it properly, then your organs and the organ systems and those parts are literally lighting up, and it lets them know that they can get a visual of what exactly is happening on the inside. They could also inject it into your through an IV into your bloodstream, and effectively the same thing would occur. So it's one way to get a diagnosis on what's happening without having to do invasive surgery. But you would want something radioactive to not stay in your body's system for too long. You want it to break down very, very, very quickly. So if you look at this example here, starting off with 80 grams of an elemental isotope, 45 hours later, so you're looking at approximately 2 days later, you've got 0.078 grams. So you've got about 8/100ths of 1 gram. You've got 78 1,000ths of a single gram remaining in your body, because the rest of it has broken down into a more stable form that will theoretically cause you less harm. And so in this case, the benefits outweigh the costs. And then we do this all the time in medical diagnoses. This is one way to do it. So just so you know, that's one application for these things. And when we have something like that, it is called, sometimes you'll hear it called a medical tracer. So if you trace something, you kind of follow its path. So a medical tracer, something like this, some sort of elemental isotope that decays very, very rapidly, fairly rapidly, would be a way for a medical professional to be able to trace the path of the molecules that are being broken down in your body, that are traveling through your body, so that he or she could get a better idea of what may or may not be your ailment, what's causing you to be sick, to not feel so well. So just a little filler information there. All right, hope this was helpful. Work on those practice problems. Always great learning with you. I will see you in another lesson really soon. Take care. Bye.